ought to be getting into the having to respond and say it's being recorded. And we'll go back to that share screen. Okay. In the notes I gave you, which we will be looking at a little bit more, we proved that the constant function had a certain limit, that the straight lines have certain limits, that various other things have certain limits, but the main idea was to show you how to use the epsilon delta argument. And then we want to get away from that for concrete things, like if I had this problem to do, the notes tell me that the limit of a product is the product of limits. The notes tell me the limit of the sum is the sum of limits. The limits of the difference is the difference of limits. So when I see this thing here that my pen is pointed toward, that's a polynomial of degree 2. That is the sum and difference of more simple expressions. And so if I know that the constant function, that's f of x equals x, if I know the constant function has a certain limit as I go to 2, and if I know the product, so if I know what happens to x, not x squared, just x, as x goes to 2, what happens to x? Well, yesterday we said that goes to 2. So if I know that, and I know the limit of the product is the product of limits, then I know what x squared does. I don't have to prove it, I know because I just multiply 2 times 2. If I know what x does, I know what 7x does, because one of the things in that note stuff is that a constant times a function. If you know what the function does, you know what a constant times it does. And this is a constant function itself. It doesn't change. And so I have the sum and difference and product and scalar multiple, we call it. That makes up this polynomial, is all those different ways of combining. And the theory I gave you says all you got to do, because you know all that, is stick the 2 in this whole thing and see what you get. So if you did that, you'll get 4 plus 14 minus 5, which I think is 13. So when I later see this, I'll say, hey, that's a polynomial. It's continuous. If I have to take a limit, I just stick the number in. That's what we'll do later. Now, however, it is instructive for you to try to do something like this, even though we just found out you don't have to. It's instructive to try to do something like this with epsilons and deltas. And the reason is it's a little bit more complicated than what we talked about so far. Now, in the notes, it actually does x squared in general, and that's just as complicated, but let's see what happens here. Now, I tried to tell you, and I hope you start getting used to this, for every epsilon, there's a delta, such that, and all that. That ought to become part of you for this class, like it or not. It's good. I will put it on a test. I'll ask you to state it. And then later I'm going to publish all the answers that you give me because of all the interesting things that you think it says rather than what it does say. Best thing to do is just learn what it says and write it down. Anyway, you take an epsilon. Anytime we have to prove something, for every epsilon, we start out with 1. The next thing you have to do is to find a delta. Now, at this stage, I have no idea how to find the delta. What I write here is something we do after we do something over here. Okay, so this idea here is going to come to me after I play with what I have to deal with. And what do I have to deal with? I have to prove an if-then sentence. And the part of that is I'll be given the if part. I have to verify the then part. And what I've written down here is part of the then part I have to verify. I have to make this thing, this is f of x right here, minus L. F of x minus L. That has to be less than epsilon. So I'm going to take that and play with it. Since it's algebra, what do you do with algebra? You factor if you can. And if I look at this expression and simplify, this is f of x here, there's a minus 5, here's a minus 13. I can combine those. So I do that, I get this expression. And with a little thought, I see how to factor it. Now, why is that important? Because when we do the if part over here later, I'm going to assume that the x I'm heading toward is less than delta. Here is x minus 2 right there. Here it is over here. That's good, because I'm going to know this is less than delta. Okay, so this expression, which I have to make less than epsilon, is less than delta times x plus 9. Now, what I might think to do, now I'm going to do something that's wrong, so let me do it right here. What has worked for us when you have, like, if f of x, this is from the notes now, but if I had 3x plus 2 and you're given an epsilon, we found out that the delta that works is epsilon over 3. It's this number right here that you can choose to let you choose the delta. That's what the proof of that section in the notes said. And that's because if I do the then part here, if I do the limit as x goes to 2 or something of 3x plus 3, and I figure that out, that's 6 and 3, that would be 9, because that's a continuous function. You get to stick in where you're going. What's the then part? The then part would be 3x plus 3, that's f of x, in this case, minus a 9, that's the limit. I worked the algebra out on that. That's 3x minus 6. That's 3 times x minus 2. Hey, there's my x minus 2 coming in again, because I'm heading to 2. So I'm going to have an x minus 2 here less than delta. You can't see that. So I'm going to, this is what I'm going to have in my proof when I get to the proof. So I'm playing with the then part here. The then part tells me this. That's got to be less than epsilon. So what you do is you say, okay, when is 3x minus 2 less than epsilon? And the answer is when x minus 2 is less than epsilon over 3. So you make the delta epsilon over 3. So we go from the playing with the then part and we see, hey, I can figure out what the delta is right here. Okay, let's go back here. Here I've got delta, but I don't have 3. I've got x plus 9. I got an x there. But for people with no experience, you think, okay, I'm going to make delta x plus 9 less than epsilon, like I did before, just a few seconds ago. And that means the delta is less than epsilon over x plus 9. What did I do over here? I made epsilon over 3. What am I doing over here? I'm doing epsilon over x plus 9. Now, is that legitimate?
I'd say no.
And it's not legitimate. Let me show you why. In the proof, so suppose that in the proof, and here's the proof now, I have an epsilon, you choose a delta. Suppose I didn't choose a delta like whatever's under my finger. Suppose I chose it to be epsilon over x plus 9. Okay? Suppose right here I say delta is epsilon over absolute x plus 9. Suppose that's my choice. Right there. Now, what I hope you'll notice in the logic of the proof, when do I choose x? If you remember, it says for every epsilon greater than 0, there is a delta greater than 0, such that for every x in the domain, that's when I choose x. I choose x right here. Let x be in the domain. This is where I choose the x. What is this x up here? That is an x before I choose x. Logically, that makes no sense. If I don't pick something, if I don't buy a stock until tomorrow in the stock market, then I can't say I made any money today. I cannot. This x does not exist yet because I haven't chosen it yet. The definition is very careful. For every epsilon, there is a delta. That's first. Then you pick the x. You can't let delta be something with x in it because you haven't picked the x yet. You see? If you haven't yet picked a spouse, you can't talk about the spouse that you haven't picked yet. If you don't know who you're going to marry, you can't talk about the spouse. It doesn't make any sense. So the thing that worked for straight lines, the thing that worked for picking epsilon, delta to be epsilon over 3 here, that worked from this work, does not work for x squared. That's why on this page, I got a bunch of extra junk here. This is why it gets harder, and this is why we try to avoid it if possible. Now, here's the key. This is where I am. This is what I know about the size of things. But I get to choose delta any way I want, as long as it works. So I'm going to decide arbitrarily to pick the delta to be smaller than 1. My choice. You can pick it to be smaller than 5 if you want, or smaller than 1/2, or smaller than 1/10. You can pick it to be anything you want, because it's going to turn out to be okay if you do that. I didn't say what it is. I said it's going to be less than or equal to that. So I'm going to choose delta to be less than or equal to that. And then I'm going to say, okay, when I get to this x minus 2 is less than delta, I will know that this number is less than or equal to 1. So I'm going to play with that. If x minus 2 is less than or equal to 1, then I can write minus 1 is less than x minus 2 is less than 1. I can add 2 to both sides and get 1 is between x and 3. And I can add 9 to everybody and get x plus 9 is between 10 and 12. What was my other finger up here? What do I have over here? I have x plus 9. See that? X plus 9 is between 10 and 12. So what's absolute x plus 9 less than? The answer is 12. So what I can do because of this right here is go back up here and say, this will be less than 12 delta. Now I can set that equal to epsilon. So now we can maybe understand why I chose delta to be the smaller of 1 or epsilon over 12. Where did 12 come from? It came from saying I'm going to pick the delta to be smaller than or equal to 1. And when I do that, that says x plus 9, therefore, is smaller than or equal to 12. So I choose delta to be the smaller of these two. And then I try to do my proof. Namely,
What did you do with the 10?
I'm sorry?
What did you do with the 10 on the?
I'm lost.
10 is 10 is less than x plus 9.
Yes.
What happened to the 10?
If I make delta, let me just go through and see if we still have the question. If I make delta less than 1, when x minus 2 is less than 1, I get this. If I would add 11 to everybody, I would get 10 is less than x plus 9 is less than 12. If I know that x minus 2 is bigger than minus 1 and less than plus 1, I know the x is between 1 and 3. So x plus 9 is going to be between 10 and 12. Okay. So that's going to be less than 12, which I go back up here and say, okay, then this will be less than 12 delta, and that's going to be part of my choice.
Okay, I get it.
Now, I'm trying to show you something complicated, okay? This is not something you just look at once while you're eating ice cream or something and you get it. You have to think about this. And it's because it gets complicated that we develop theorems to avoid us having to do it. Mathematicians are very smart people, and they don't like to work. They like to avoid work. So they figure out how to do something in general so they don't have to do it specifically many times. Okay? So anyway, this proof now, if I assume this about, and delta assumes to be this, then when I play this game, now I'm going to go back over here. This work over here is not just nothing. I'm going to copy it. This is equal to that, which is equal to this, which is less than or equal to this. And that's less than this because I mean, how do I know this less than it then? Because the delta is less than 1. Now remember, the delta is less than either one of these, so it's less than both. So it's less than 1, which makes me allow me to do this step. And because it's less than 1, I can replace this with 12. And because the delta is also less than epsilon over 12, I have 12 delta. I can replace that with epsilon over 12 and get epsilon. So anyway, I wanted to show you a more complicated proof, which we can avoid by learning that the limit of a product is the product of limits and limit of the sum is the sum of limits and all that. We have theorems that make it easy for us to get the answer 13 here without proving. But if I have to prove the epsilons and deltas, this is the proof. Okay. Now, we don't do x cubes and x fourth powers and x fifth powers. Why not? Because we have theorems. X fifth power is x 5 times. Okay. If I know what the limit is once, I know what the limit is times 5. So anyway, that's what I wanted to show you there. You might be responsible for something that bad, but nothing worse. That's good and bad. I like to give you things that are good and bad at the same time. Okay, so new page. What do all those notes we did tell us? Well, if I have x to the nth power and I'm heading toward the number a, all I got to do is stick the a where the x was, and that's the answer. That's because of the notes. The limit of the product is the product of limits. Okay? Now, that does not mean that we know what if the n is the square root of 2. That does not mean I know what x to the square root of 2 is. We haven't defined that. But what we know is x squared, x cubed, x fourth, x fifth, x sixth. We know those. So we have a restricted thing here. We don't know about x to any power. We know about x to a positive integer power at the moment. But we also know the limit of the sum is the sum of limits, and limit of a constant times a power is a constant, so on. Anyway, we know polynomials are continuous. You have a polynomial, you stick in where you're going. What about rational functions? Rational functions are the quotients of polynomials. Well, we have a theorem that says the limit of the quotient is the quotient of limits. So if you're heading to some place where the denominator is not 0, then the limit of the quotient will be the quotient of the limits. So what you do with a rational function, if the denominator isn't 0, is you stick the number in and get a fraction, and that's the answer. So we know that the rational functions are continuous. You get to stick in where you're going. Square roots, we have proved in the notes, are continuous. So where does the square root of x go? If x goes to 9, it goes to the square root of 9. You just stick the 9 in there, and that's 3. Don't have to prove it. We've already got it. We don't know anything about cube roots or fourth roots or fifth roots because we didn't prove it yet. Okay? But the proof I use for square roots, the same proof will sort of work with a little bit of change for third roots and fourth roots and fifth roots and sixth roots. So if you want to do all roots, you've got to do some epsilons and delta proofs. Okay? Now, in this section, the author talks about something called infinite limits, and that can mean two different things depending on how people interpret that. And also, we talk about one-sided limits. So I want to talk about that real quickly a little bit. We'll be talking more about it. Okay, now let's go back to what I've been talking about, which is more than what the author is talking about. We have what we call accumulation points of a set. Now, by the way, when you write that out, that takes a lot of writing. So we make it simpler by saying we put a little prime on the D. If the domain, if the set is D, if you put a little prime on it, that says any member of that set's an accumulation point. That's just so you don't have to write out everything I wrote out there above there. See if I can make this, don't know if it's brighter or not. Anyway, okay, what's an accumulation point? It means every neighborhood of the point contains at least one point from D different from X naught. Okay, now what I want to do is enlarge that definition a little bit. Hopefully it will focus. Come on, thing. Okay. What do we mean by saying infinity is an accumulation point of a set? This is not in the book. What do we mean? Because the book doesn't talk about accumulation points at all. What do we mean when we say infinity is an accumulation point of a set?
Well, what we're saying is that x naught, I guess, is goes on forever. So it's essentially
Okay, now
it still
X naught
is
doesn't,
part.
well, slow down. X naught doesn't move.
Okay, so
But what you want to say there is we're allowing X naught to be infinite.
also the x naught has an infinite as any value as
Yeah, okay, but what do you mean by saying a neighborhood? It turns out that a neighborhood of infinity is a ray. What's a ray? It's a fish or a thing that swims. No. What's a ray? It means
well,
in the number system, something bigger than or equal to. In other words, if I talk about the numbers from 1 to infinity, that's called a ray. If you like, it's a line that starts somewhere, but it doesn't end. It's not a line segment. With line segments, we think they start and stop if you're drawing one. But if you talk about a ray, we're talking about something that starts somewhere but keeps going. We can have two kinds of rays. They can go off to the right forever, or they can go off to the left forever. Now, what I'm saying is not very mathematically precise, so we say the interval, intervals can be infinite in length, so that's actually okay. You start somewhere and you keep going. That's what this means. So it means all the x's bigger than a. That would be an open ray. If I had all the x's bigger than or equal to a, that's a closed ray. Anyway, if every ray contains a point of D, then we say infinity is an accumulation point of the set. Now, we mean when we talk about, let's make the number 5, if I say 5 is an accumulation point of the set, that says put an interval around the number 5, any interval of your choosing. There has to be something from the domain inside that interval. In other words, points of your set get close to 5. What do you mean by saying infinity is an accumulation point? You mean points of the set get close to infinity. What's that mean? That means they get big. Now, if we think about, let's say, having a river, in order to cross the river, you want to have some rocks in the river. The rocks have to be close enough to step on so that you avoid the water. And so this is a rough, not very good analogy to an accumulation point. When I say infinity is accumulation point, you can think of infinity as the other bank that you're trying to get over to. You're only going to make it over there if there's enough rocks to allow you to get close to the other bank. And if you think of the other bank as being at infinity, then you need to have some rocks going all the way out to infinity. And those rocks are points in the set. So when you say that infinity is an accumulation point of a set, that means the set contains numbers that get bigger and bigger and bigger and bigger and bigger. You say a set is bounded if you can put the set in a big interval. If you can't put the set in a big interval, it's unbounded. If it's unbounded on the right, so that numbers that are bigger than 0 are always in the set, not every number, but something, that's called an accumulation point of infinity. Now, if we allow that to be an accumulation point, and if we allow minus infinity to be an accumulation point, then we only need one definition for limit, because we only take limits at accumulation points. So by allowing infinity to be an accumulation point, then we can talk about limits at infinity. Now, what else can we talk about? We can talk about limits at minus infinity. And then you could talk about this. If x naught is a finite number, like 5, and I put a little plus on it, I mean stay to the right of 5. Stay bigger than 5. So this little idea has to do with being bigger than 5. If I put a minus on things, that means less than 5. This isn't an exponent. It's just an attempt to say stay on the left-hand side. And that will allow us to do left-hand and right-hand limits. In other words, if I get close to 5, but I always stay bigger than 5 by getting close, like if I'm on one side of a cliff and I always stay over there, okay, then whatever the functions involved on that side, we can talk about a limit as you approach 5. So as I approach the edge of the cliff, you'll have a certain altitude. As long as you stay on one side, you're not going to go off the cliff, okay? On the other side, maybe you have people at the bottom of the cliff on the other side. They're not going to be ever at the top, but their altitude is at the height of the bottom of the cliff. That's a left-hand limit. So we can have right-hand limits and left-hand limits by restricting where the x is. So I'm going to try to show you here what we're going to have beneath our symbolism. This says x goes to x naught. This says x goes to x naught from the right, meaning all the x's are bigger than x naught. This says you go from the left. That means all the x's are less than x naught. This says we're heading to plus infinity, and this one says we're heading to minus infinity. Now, the text needs 5 different definitions. We only need 1. So however bad this epsilon delta definition is to you, it's not 5 things, it's 1. But what we do in this definition, now I'm going to repeat it, for every epsilon there's a delta such that for anything in the domain, if then. Now, the if part is what we are changing. The thing I have my finger under right now is the thing you supposedly already learned. This says x is close to x naught. It's a distance less than delta between them. What's the one I'm going to show you next say? This says x minus x naught is bigger than 0. What does that mean? That means x is bigger than x naught. Suppose x naught's 5 and x minus 5 is positive. Then x is bigger than 5. Okay? If you have $6 in your pocket and there's something costs $5, you know you're okay because the difference between the two is positive. And you can buy the thing if that's what you want to do. So this, if I replace absolute value of x minus x naught with just x minus x naught, now I'm saying right-hand derivative, staying on the right. If on the other hand, instead, I write x naught minus x, if I turn them around, now I'm staying to the left. This is the definition you put in. You put, for left-hand derivative, we insert this in instead of the one up here. Nothing else changes in this definition. If I'm going to infinity, then now I'm thinking about being bigger than something. The x has to get big. And so now instead of thinking of delta as small, I think of delta as large. So if I'm doing limits to infinity, I would be in the if-then sentence, I would be putting this as the if part. And if I'm going to minus infinity, I'd be putting this as the if part. The delta is still positive, but I'm less than minus delta. That says I'm very negative. Now, so we have 5 different definitions into one if you just tell me which one you want to talk about. It gets worse than that because the limit can be infinite or minus infinite or finite. We have three different kinds of limits we can have. And what kind of limit you have changes the then part. So to hit you with as bad as it gets, what the author will have is 15 different definitions. We have one definition which you interpret. So what I've been talking about is the first five. And that's when, and see, if you look here in this, I left out what it is. If I put L in here for limit, if I put an L in here, this absolute value of f of x minus L, if I put L in there, that's the regular definition you've been thinking about up to now. But suppose I want to say the limit L is infinite. If you take a polynomial like f of x equals x squared, what happens as x gets large? As x gets very large, x times x gets even larger. So what we would write in that case is the limit, okay, as x goes to plus infinity, as x gets big, what does x squared do? It gets very big. So we would write the limit of x squared as x goes to infinity is infinity. That's at the bottom here. But we haven't defined that yet because the thing up here assumes the limit is finite. So I'm going to have three different things I can put here in the then part. One is f of x minus L. That's when you think the limit is finite. Or f of x is greater than epsilon. That's when you think the limit is plus infinity. Or f of x is less than minus epsilon if you think the limit is minus infinity. We'll be talking about these. But what I'm trying to hopefully get you to understand here is this is complicated. It's the same statement, but there's 15 of them. You can collapse that to one if you learn how to substitute the difference when you change from one kind of limit to another. You might have to change the two things here you hopefully have already studied with one of these. And if you do that, you have an easy way to remember 15 different definitions, but you're going to have to remember the first one. And you will be tested over this kind of stuff. Okay, so that I wanted to say, I want to go to WebAssign today, and it's 10 after. So maybe I can postpone what else I was going to tell you about here. Let's go to WebAssign. If I can share a screen, I'm going to turn this share off, so you're going to see my ugly old self here for a minute. And I'm going to share a different screen, hopefully. Okay. 4 of you I noticed had started looking at section 5. And I want to tell you some things about section 5. Now, one of the things I want to do in this class is go through the homework with you, is do some of it with you. It's very helpful if you try to do it ahead of time and mark the ones that are like, whoa, I don't know what to do. Okay, those are the ones we ought to concentrate on. If you look at an assignment and you can do them all, we don't need to look at it at all. If you know the stuff, we can skip it. On the other hand, you don't want to lie to yourself, because I'm going to look for the ones on the test that I don't think you know how to do, just to bug you because I'm a mean person, okay? And so what I said here in this instruction set is take a look at these, okay? I have one person I noticed just looked at them, and so maybe you've done that. I have several things to point out, okay? So I'm going to get to that and try to point them out. So, okay, problems 1 to 5. In fact, problems 1 to 12, you're going to find are what I consider to be easy. Okay, so let's look at them. I got to expand this, and of course, I'm cheating because I have all the answers. So I can do these real quick. Okay, I just have to choose the one the author did to be right. I got to have that much intelligence. We've tried that, by the way. We have sometimes given students a test that's all filled out already and asked them. And we have some of them count stuff wrong because they don't think it's right, and then we find out that sometimes students don't pay attention to that, to having the answer sheet. Anyway, with there we have videos. Now, what's this? I included these videos when the author does. The author, I'm not going to do this to take the time, but the author, this is the author of the book. Unfortunately, he died. So this is not him dead, this is him while he was still alive, okay? It would be a kind of morbid otherwise. Anyway, he gives you a video and he likes to talk. I do too. And then he asks you a question, okay? I suggest you try to do the question first and then watch the video. It says watch the video, then answer the question. I hope that you don't have to watch the video. But anyway, the vertical asymptote. Okay, you and I haven't talked about that yet. We're going to talk about it, but a vertical asymptote comes from the fact that the denominator might be 0. Okay? The trouble is when the denominator is 0, that's when x is 5. He writes y equals 5 over here, and that's why that's false. Now, you guys get 3 chances at these problems, and there's only 2 possibilities. So anybody who doesn't get the question right in 3 chances probably should drop the class. Okay? Because I don't think you're going to make it. But anyway, I'm putting these in to be helpful. Whether you take the test or not here is true, which you'll get it right. That's a point for you, big deal. Okay. So why do I say these are easy? Because they give you multiple choice, and you should know by now, this says x is near 2, f of x is near 5. So you look through here and you see which ones will work. And of course, when you read this one, I hope you'll say, yes, this makes sense. The values of f of x can be made as close to 5 as we like by taking x sufficiently close to 2. I hope when you read it, that this makes sense to you. But the whole reason for the problem is to help you see what should make sense to you. Okay? So you don't have the answer, I do. But when you read through these things, one of them ought to make more sense. So some of the original are just asking you about stuff. This is why I call them easy. We talked about holes in the graph yesterday. You might have to think about this a little bit longer. Tomorrow, when we have more time, because it's 15 after already, we can talk about these problems if you look at them. But for the first 10 or 12, well, the first 4 anyway, they're sort of asking you questions. Now you get some pictures, and you're supposed to be able to figure out when x goes to 2, now what's this little minus? That means from the left. That means you're talking about stuff over here, because this is from 0 up to 2. So this first question does not involve, I can't cross out, but does not involve this stuff at all. Only involves this part. So as x heads to 2 from the left, what happens to the height? Well, if I look at it, the height is 3. So that's be my answer. I hope that's an easy question. Okay? So he goes through asking you some questions. Here's a does not exist. Why does this not exist? Because the left-hand limit is 3. The right-hand limit looks to me like it's 1. And therefore, the left and right-hand limits are different. Aha. That's actually a theorem in the book, that if the left and right-hand limits are different, the limit doesn't exist. So your answer to the third one, if you know that, if you've answered the first 2 correctly, these are different. That means this does not exist immediately. But you might have to be told that, or you might have to read the text. That's one of the reasons I want to go through it with you. I want to tell you what I see as I go through. Okay? So anyway, you have some problems like that. And then you get to this one. This is like a graph. I mean, suppose you have a graph like this. Well, whether you can understand this very well or not, I'm going to tell you there's no limit in here. As you head to 4, this thing oscillates over and over. So actually the graph approaches every number between 2 and 4. You can't have graphs approach more than one number. So when you see some kind of a beehive thing like this, there's not going to be any limit at that spot. Again, these are things we have to go through, and I'll have to talk more about that. That usually involves something like sine of 1 over x as x goes to 0. That's when you get oscillation like this. That's the new wrinkle in this problem. Okay, sorry, I don't know how I lost that. I think I used too many fingers on my screen. Come on, screen, catch up. Okay, so you have some questions like that. The author, if he means for you not to assume that, I mean, this graph is an open thing. It doesn't end up at 2. It just approaches. So here you have a function at 2. This is the definition. This is f of x. This is f of 2. The left hand doesn't go up here in the right. So we have a right hand limit and a left hand limit that's not equal to the function value. That means the function's not continuous. Now, the author in this section doesn't have continuity yet. So he can't ask you that question. But this is an example of a case where you have a jump discontinuity and the limit is not equal to what happens on the left and right. So you don't have a limit. If you don't have a limit, you don't have continuity. It is defined there, but it's not continuous there. Okay, so we have some pictures and you're going along and you think, okay, I'm pretty good. And then all of a sudden you get to number 12. I think let's see, what's the problem? Problem 13. You're going along, everything seems to be going good, and you get to 13. Now, look at the function here. It's 19 after, but look at this function. I have 2 to the 1 over x power. The author is a dirty person as far as a teacher. We have no way to know what this is. We don't know what this is until we've defined the exponential function and the logarithmic function and what we mean by powers, real powers. Now, we can do the problem, but you have to think harder. So all of a sudden, in the middle of these other easy problems, he sticks this hard problem, kind of, relatively speaking. I don't mean it's really hard, but it will throw you for a loop because you're not expecting it, okay? Now, what you're supposed to do here is to say, okay, what happens to 1 over x as x approaches 0? Now, if you know 1 over x, I'm going to try to draw it. When x is positive, it looks like this. When x is negative, it looks like this. What happens at 0 is on the right-hand side, you're going to plus infinity. On the left-hand side, you're going to minus infinity. So what they want you to do here in your mind is approach 0 from the left. And the 1 over x is going to minus infinity. What is a number to minus infinity? It's 1/2 to plus infinity. 1/2 to plus infinity is 0. And so this thing, because it's continuous, but the author hasn't done that section yet, it goes to 4 over 1 plus 0. And that's why the answer is 4. But I would not expect you to be able to do this problem with what we know. Okay, unless you really think hard about it. You can figure it out, but this one is out of place. And so when you do these exercises, if you find something like, whoa, what's he doing to me? You're probably right. Hannah Kraus has entered the waiting room. I didn't take your guys' picture yet, did I?
No, not yet.
Hannah's with me. I don't know why it says that. I'll admit, I'll hit this in a minute, but Hannah's already here. I need to take a picture of you guys before we lose anybody. So I hope we haven't lost anybody yet. Let me take your picture and I'll get off the, just a second. Okay, I'm also going to stop the recording.